I have a question. I see a circle on the board.
Yeah, it does.
It reminds me of something.
Uh-huh.
There was something we had to do in art class in 8th grade, which is to draw a flower.
Yeah.
And the way we had to do it was to take that radius of a circle.
This, yeah.
And put any point on the circle.
Okay.
And then with that, using that as the radius, cut off points on the rest of the circle.
Wait. Let's do that. Let's do that.
Oh, you want to do
correctly?
it?
Yeah. Let's see that. Yeah. So this is the radius. This is the radius.
Okay.
And
now
now
from
I
that
put this
point
here.
you cut, yes.
And do this.
Right.
Okay.
Then you go to the next point, the point, one of the cutoffs, and
Here.
do this, do
Okay.
the same thing,
Uh-huh.
and repeat that.
Uh-huh.
Okay. All right.
Okay. And then do this.
Once more.
Do that again.
Once
Okay.
more.
And do that here. And oops.
Okay, and I think once more.
Here.
No, that
No,
one.
we did that.
that one.
Okay, and this one.
No, from here.
From there.
Okay. And here and oops. Here.
Okay, I guess to get it perfect,
roughly.
you need to get it perfect, you need a compass.
Right.
But
This will come. Yeah.
The
You will
thing
get
is,
a 6-petal flower if you do that
see,
with a real compass.
Yeah, but then are you going to get it every time you do this?
Are you going to get a perfect 6?
A perfect 6-petal flower every time you follow this.
So if I make the circle smaller or bigger, if I draw it here.
If you do it 2 million times, you're going to get exactly the same.
So that looks like a mathematical problem.
It's surprising that the last one you do meets here and here perfect.
That's right. Yeah. Yeah, that's interesting.
And if you change the radius even slightly, if you make it bigger from the original thing,
then it will never match.
It'll never match. So why does this happen? Why does that?
This is the radius, right? This is the radius.
Yeah.
Radius. And when you put it here and do that, then this is the radius.
Yeah.
So the question that you're asking is, if you have a circle with radius r, and you take the same radius and do this, and then the same radius and so on like that, it'll divide it.
You'll get 6 lines. You get a hexagon.
So that's what you get here.
You'll get a hexagon.
In fact, you get a regular hexagon. That means all sides.
Yeah, so the question is, how come it's a regular hexagon?
Regular means? What's a regular hexagon?
Regular hexagon is one where all the sides of the hexagon are of equal length.
Okay.
And it is convex.
All sides are equal.
No, all sides are, at least 5 sides are equal is obvious because it's the radius, it's the same length.
You mean 6?
But the question, the question is, how come the 6th one lands exactly at that spot?
Yeah, so it's not surprising that these 5, because this is how we started, these 5 being equal is not surprising, right? Because we first put it
we did it that way.
We did this way. This is radius, this is the radius, then we did this, then we did this, then we did this. So till here it's not surprising. The question is, why is it that even the last one here
is the radius?
Yeah.
So if you can prove that given any circle,
Actually, can I
it
put
can
it
circumscribe a hexagon.
Can I put it slightly differently? That is the radius because you're doing it that way.
Yeah.
The question is, how come it falls on that point where you started?
Yeah.
Right.
So why does this radius not? Why does this one not end here or here?
Yeah.
Why does it end perfectly here? Is the question.
Yeah. And if you can prove that given any circle, inside it you can draw a regular hexagon with all the 6 sides equal, then that seems to be the same as what you're saying, that if you take radii, 5 radii, and then this will also be radius.
Yeah, so we want to show, no, what we need to show is that not that you can draw a regular hexagon, but that you can draw a regular hexagon with the radius as the
radius,
side.
that's right. With the radius equal to the sides.
Yeah.
Six sides, all equal to.
Yeah. So notice here, as you said, this is the radius, but this is also the radius.
Yeah.
Right?
No, hold on, let me write the conjecture.
Yeah.
To prove it. So how would you formulate the conjecture? For every circle, or every circle circumscribes a regular hexagon
Whose sides are equal to.
Whose sides are equal to the radius of the circle. So we began with drawing flowers and we ended up with a mathematical conjecture.
Can I say that if you, like I said earlier, if you draw it say 2 million times, every time you're going to get this, and therefore it must be. I have proved this conjecture.
So you proved it scientifically once again, but a mathematician is not interested in that, because it could be that if you did it on Pluto, it wouldn't be the same, right?
Yeah.
And you did it on a piece of rock rather than a piece of paper, it wouldn't be the same.
Yeah. So we did this on the green board.
Yeah.
If you do that on a piece of paper, will that be true?
We don't know.
Yeah. So how do you prove this conjecture?
Yeah. So
we can actually remove the flower there.
We can leave it for now.
Yeah. Okay.
Oh, it's okay. So as you said, this is the radius, but this is also the radius, right?
Okay.
So that means all the 3 sides of this triangle are equal.
That's right. So it's an equilateral triangle.
And it's an equilateral triangle.
Yeah. So let me write that. Equilateral.
So let's label
triangle.
the points. Let's label it A, B, C.
Well, let me remove the unnecessary parts because that will cause some confusion. These things. So we are not talking about not anymore about the flowers, but about the hexagon.
This one.
Yeah.
This we don't know what the length is.
Oh yeah, right. So we leave that.
Yeah.
Yeah.
So
that is also an equilateral triangle. That's an equilateral triangle. That's an equilateral triangle. So what we have, this we know this is R and this is R. So what we have to prove is that this is also R.
or this is an equilateral triangle.
Yeah.
Then we get that.
Then yeah. Okay.
So here you have this is radius R, this is radius R, so it's an equilateral triangle. So what I'm going to say is that all equilateral triangles are equiangular.
There is a theorem. Okay. There is already a theorem, right?
Yeah.
A theorem is all equilateral triangles are equiangular. Yeah.
Don't you also have a theorem that says that the angles in a triangle are equal to 2 right angles?
The sum of angles.
The sum of angles, yeah, the sum of angles.
Okay, why are you saying that? There is a theorem like that.
Yeah.
The sum of angles of a triangle is 2 right angles. So you're saying that you will use these 2 theorems to prove that.
Yeah.
Okay.
So here we have all equilateral triangles are equiangular. So this angle is equal to this angle is equal to this angle.
Okay, fine.
Okay.
Yeah.
The sum of angles of a triangle is 2 right angles. So this angle OBA.
So each of them has to be 2/3 of a right angle.
2/3 of a right angle.
Yeah. So
okay.
So plus angle BOA plus angle BAO is 2 right angles.
Okay.
So 3 and since all these 3 are equal, you can just replace this by 3 times angle BOA.
Yeah.
Equals to right angle. So angle BOA, as Dara said, is 2/3 right angle.
So all these angles.
All these angles.
This angle, this angle, this angle, this angle, this angle,
Yeah.
this angle, this. But I
That's
don't know
it.
about
We don't
this.
know about this.
But this.
Yeah.
All these are 2/3 of a right angle. This
Yeah.
we don't know.
But,
So
but,
this
but
is, yeah. Yeah, Tara?
in EOF,
EOF. Yeah.
you have 2 of the sides are the radius, so they're equal.
Yeah.
These 2.
Which means that angle OFE and OEF must be equal.
These 2 are equal.
These
Okay.
2 are equal.
But we
Okay.
don't know if these 2 are equal to this.
Yeah.
No.
So that's from another theorem that
Yeah.
in an isosceles triangle, the angles opposite to the equal sides are equal.
Theorem 3 in an isosceles triangle, the how does the theorem say? The angles
Angles opposite to the equal sides are equal.
opposite to the equal sides are equal.
Yeah.
Hang
What is an
on.
isosceles triangle?
One with 2 sides equal. At least 2 sides equal.
Okay.
Isn't there another theorem that says the angles in a circle in the center, in that circle in the center, angle, all of the angles in O put together give you 4 right angles?
Yeah, let's come
Yes.
to
Something like that.
So what we get is this angle is 2/3 of a right angle. 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 And this angle is 2/3 of a right angle.
Yeah.
So this angle from here to here is
10.
1, 2, 3, 4, 5.
10/3.
Is 10/3. So this big angle. 10/3 right angle.
And the theorem that Tara mentioned, actually, we had talked about it earlier,
Yeah.
that if you have a full rotation,
Yeah.
this
That's
side,
equal to 4 right angles.
that will be 4 right angles.
Which will be 12 by 3 right angles, right?
So this will be 4 right angles.
So the entire thing is 4 right angles.
Yeah.
So the entire circle is so the circle
Yeah.
is 4 right angles.
Of which these 5.
These 5 you can, so in order to get this, if you subtract the angle of these 5, you'll get you get this angle. So that angle FOE is 4 right angles minus 10 third right angles, which is 2/3 right angles. You'll be able to figure that out.
You mean if you subtract this from here, you get
You get
2/3.
2/3 right angles.
4
Okay.
4 right angles is 12 by 3.
4
This
right
is
angles.
minus
This
10 by 3 gives you 2 by 3,
is
right?
12 by 3 minus
10 by 3.
10 by 3
2 by
is 2 by 3. Yeah. You
So
will
this
get.
is 2. So
So
this
that's-
angle is 2/3 of a right angle.
Also 2/3.
Oh, so all the angles are equal.
Yeah. this angle is equal. So now what you know that this angle is equal to this angle, and this is 2/3 of a of a right angle.
So that means all sides are also equal.
And the sum of these three is two right angles. So we get 2/3 right plus, let's say this is x, and this is also x, plus 2x is two right angles. So 2x, we can subtract 2/3 right angles from both sides, you get 4/3.
So that's
right
2/3 and
angle.
2/3.
So x is 2/3 right angle.
Yeah.
So each of these is also 2/3 right angle.
That's an equiangular.
So now this is equiangular.
And equiangular is the same as equilateral.
Equilateral. So this is an equilateral triangle, and this therefore is
that'll be an R.
But your theorem 1 only says all equilateral triangles are equiangular. Doesn't say that all are equiangular.
Yeah, but there is another theorem that says all equilateral triangles are equiangular. There is another theorem which says all equiangular.
So we need a separate theorem for that.
Yeah.
Yeah.
So let's call it theorem.
Can you just say
Theorem
all and only equilateral triangles are
That will
equiangular?
have the same effect.
Because then you
all
don't
and
really
only.
need.
Yeah, I think we should summarize this proof because the general structure of the proof, because there's too much stuff on the green board.
Yeah.
So,
Don't erase the conjecture.
And don't erase it.
yeah,
You can erase it.
all the calculations. Actually, we can erase this too because there's too many calculations here. Let's do this again very, very quickly. So, if you have a circle and if you have
A regular x.
yeah. So what we did was to say these are all radii, and this is radii, this is radii. All these are radii. So this is the part that we
So let's do a dotted line.
dotted line, and we said these are equiangular because they're equilateral. These are equiangular. These are equiangular. All of those.
Yeah.
Because of that theorem.
So from theorem 2 and theorem 1, we concluded that this angle is 2/3 of a right angle.
And
all of these
together will be
10/3 of a right angle. 5 times 2/3 of a right angle.
Right angle.
And so what is left here from theorem, where is that? We didn't
no, but once we say this is, once we calculate this, we can calculate this. We prove that this is also 2/3.
Yeah, but we proved it. We haven't written down the theorem that the total circle is four right angles.
Yeah.
So this will also be 2/3 of.
And then if this is 2/3 and if this and this are equal, then those are also 2/3.
Also 2/3.
And therefore they are
Therefore this is equiangular.
Equiangular,
and therefore it's equilateral.
Therefore this will be R. That's it.
Yeah.
Those are the steps.
Yeah. Yeah. So notice I want to pick up on theorem 2 because we assumed we took theorem 2 as something which we proved earlier. But actually, we haven't proved any of these theorems earlier. I want to pick up on theorem 2 and try and go back.
In order for this to work, all of these are this is true, this is true, this is true, this is true.
Yeah.